The box of weight W is being pulled by a rope at angle theta above the horizontal line shown to the right. The friction between the ground and the box is represented by a constant mu. Okay? I'll just write something like mu. If the force... So two cats are sitting on a roof. Which one falls first? The one with the smaller mu. Yeah, it's terrible. Okay, focus. If the force as a function of the angle theta is modeled as this, at which angle is the force F of theta minimized? Okay, so one thing to notice is this is just F. It's not implying the integral because it's capitalized. So the interplay between forces here is mu is a function of the normal force. So we have the normal force here, which is going to be the weight, which is mass times gravity, minus F sine of theta. So basically, when you're pulling on the string, you're pulling it up, so it's not resting on the ground as hard, and that is going to have effect on how much friction it is. So if you ever think of like when you're pushing on a box, if you ever try to push on a box, you want to push it, horizontally. But if you try and push it kind of down at an angle, it's going to be really crazy hard to push. You don't do that. And like intuitively, you're like, oh, well, that's dumb. But the idea here is you're pulling it on a string. And so you're kind of lifting it up and reducing the friction as you do it. And if you think of it intuitively, if you pulled it straight up, there'd be no friction, which kind of makes sense too, because you're not dragging it. Okay. So this is our model. We could probably derive this, but it's not worth our time. So the weight, that's the mg right there. Sine of theta, I have a suspicion that comes from... Okay, not important. Focus. They've given us a magical equation. We should work with it. Okay. So we want to minimize the force here. So we want to take the derivative of this. Derivative with respect to theta, because that's what we're going to change here. We're trying to find the optimal theta. So, wow, this is challenging. Okay. So we have F of theta equals mu times W times mu sine of theta plus cosine of theta to the negative 1. So this is a constant, and the only thing that will change will be theta. So f prime of theta will be mu w times... Okay, now this is going to be the chain rule. So we'll take this negative 1, move it down here, negative 1 times mu sine theta plus cosine theta to the negative second times the derivative of the interior. And the derivative of the interior will be derivative of the first one plus derivative of the second one in this case, because they're just added together. So we'll have mu cosine of theta, make a big bracket here, because the derivative of sine is cosine, minus sine of theta. I know I'm going kind of off at an angle here, because the derivative of cosine is negative sine. Yep, and then it's just theta in the middle, so we don't have to do any crazy like another extra chain rule type thing. So we're going to rewrite this. I'm going to do one thing here. So we have this negative 1 here, and I'm going to distribute it, so it's negative plus. Okay? So maybe down here, I know it's a big F. I'm going to write it as a small f, just because that's my comfort zone. Okay. So we still have that mu w hanging around, and we have sine of theta minus mu cosine of theta, because we distributed the negative 1, all over mu sine of theta plus cosine of theta squared equals, it'll set it equal to 0 to find the maximum minimum. and we'll start dividing both sides, canceling things out. So we'll divide both sides by mu weight, which gives us 0 because it's 0 on this side. Divide or multiply both sides by mu sine theta, cosine theta squared. That goes away, and we're left with sine of theta minus mu cosine theta equals 0. Sine of theta equals mu cosine theta. And we're looking for theta here, so we'll do sine of theta divided by cosine theta, which will actually be tangent of theta equals mu. Theta equals arc tangent of theta. Mu. Not quite. Oop. Get rid of some of that. Get rid of the riffraff. Oop. Straighten this out a little bit. Move it over towards the answer so we can see it. Yeah, it's close enough. Theta equals arctangent of mu. So it's this one right here. So I'm also going to think about the extremes because you want to think about the endpoints too. 0 to pi over 2. So we're trying to, the force, if the force is function angle on it, the friction, so we're trying to find, so this is friction right here. Friction. A box weighs being pulled by a rope in both ends. The friction between the ground and the box is represented by constant mu. If the force is a function. So I think this is talking about the net force going this direction. And so when we start looking at the extremes, what we're saying is, what's the easiest way to pull this box? And so if we look at the extremes of theta equals 0, we're going to maximize the friction by pulling it straight horizontally. But if we pull it at pi over 2, we're not going to have any force going with us. Does that seem reasonable? We're not going to have any force going to the right if we pull it straight up. And so that's how, in this problem, I would eliminate the extremes, because you really don't have, this is probably a little bit more difficult than something you get on the AP exam, but maybe not something more difficult than you would get on the free response section. And so I really have no desire to plug in arctangent of theta into a mu in there. That's just a lot of pain. Don't want to bother with it. And so I'm trying to reason out why the extremes would not be the correct answer. Because what we normally do is we're like, all right, we have our x, we have our f of x, we have an f prime of x, and we look at, all right, here's the endpoint 1, here's the endpoint 2, and then we have this theta in the middle, which gave us our critical point. And we want to test the endpoint and the critical point, find out which one is either maximized or minimized. Well, yeah, in this case I don't want to do it because the equation is kind of complicated and our theta is kind of complicated. So I ruled out the endpoint. It's not 0 or pi over 2, and those aren't even possible answers. And so what's left then is our critical point. And so the critical point is going to be the answer. In this case, it is. Theta equals arctangent of mu. And that is how I would kind of approach one of these friction optimization type problems where they give you basically a magical formula. Use the formula that's magical and just given to you, but also try and look at the fundamentals of what's going on in the background to kind of understand where they're coming from. It sometimes helps, sometimes doesn't. Depends on the physical phenomenon, how familiar you are with it. So that's how you do this problem.